Hello everyone, I'm Teekshna Chaudhary from Team Tech Titans. Today I'm presenting our solution for the problem statement System Responsiveness Guard preventing system slowdowns. So in modern computing, system performances plays critical role in productivity. Whether it is a student using a laptop or a developer running an applications or a organization managing servers. So system slowdowns can cause serious disruptions. So the main problem is every operating system runs multiple processes simultaneously. Some processes are lightweight while others consume heavy resources like CPU and memory. When too many processes run together, CPU usage increases rapidly, memory gets overloaded, process scheduling becomes insufficient, and system response time increases and also application freezes or crashes. So currently most systems react only after the slowdown has already happened. So users must manually identify the problem using tools like Task Manager or System Monitor. So this create three major issues. They are delayed detections, which is the system does not protectively detect overloaded conditions, and manual intervention. Users have to manually terminate processes. And the third one is lack of intelligent control. That means the kernel does not dynamically adjust the resource to maintain responsiveness. Therefore, the challenge is to build a system that can detect early signs of slowdown, analyze system behavior, and take preventive actions automatically. This is what our system aims to solve. So the solution for this problem is we have developed a monitoring based intelligence system that acts like a watchdog for system performance. So our solution works in three continuous steps. Step 1, real time monitoring. The system continuously tracks CPU usage percentage, memory utilization, number of running processes, and resource consumption of individual processes. Step 2, intelligent analysis. The collected data is analyzed using predefined thresholds and logical conditions. For example, if CPU usage exceeds a certain limit for a specific time, or if a memory usage crosses a specific threshold, the system marks the state as potential slowdown. Step 3, preventive action. So once the potential slowdown is detected, the system identifies the processes responsible for high resource usage, generates alerts and logs, and simultaneously or suggests corrective actions. Thus, instead of reacting late, the system protectively protects responsiveness. Now let us walk through the architecture of our system. Our architecture consists of four core components. First one, data collection module. This module interacts with the operating system to collect system addresses. It gathers information such as CPU load, RAM usage, process ID and priorities, and resource usage per process. Second one, processing and analysis module. This module processes raw data and converts it into meaningful insights. It performs threshold comparison, pattern detection, and trend analysis of resource usage. And third one, decision engine. The decision engine determines whether the system is in normal state or warning state or critical overload state. Based on this classification, it decides what action should be taken. And last not but the least, response and visualization module. This module represents results to the user. It includes alerts, graphical outputs, logs, and reports. So the overall flow is system matrices, monitoring, analysis, decision, and response. So, this modular architecture ensures flexibility and future scalability. Now I will explain the kernel interaction aspect. The kernel is the central component of an operating system. It manages process scheduling, memory allocation, CPU time distribution, input output operations. So our prototype operates at the user level, but it leverages kernel provided information. It interacts with kernel level data by reading process tables, observing CPU scheduling behavior, monitoring memory allocation patterns, analyzing system call outputs. In real world scenario, this system can be integrated with the kernel to dynamically adjust process priorities, prevent CPU starvation, optimize scheduling algorithms, and improve overall system stability. Thus, our system responsive guard acts as an intelligent layer between the user and the kernel. It demonstrates how kernel and kernel aware monitoring can significantly improve the system responsiveness. So now I'll demonstrate the working of a system. So this is how it looks like without a guard system. Initially, the system runs multiple heavy processes. We observe that CPU usage rises sharply and even memory usage increases continuously. So the system response becomes slow and applications take longer to respond. This represents a typical real world slowdown scenario. Now I am running our system responsive guard prototype. This program continuously monitors system performance in real life. Here we can see the CPU usage and memory usage are being tracked continuously. Based on these values, the system determines the current system state such as normal or overloaded condition. So this system is implemented using Python. We used system monitoring techniques to collect real-time CPU and memory data. The logic is designed using threshold-based analysis and modular architecture, which makes the system lightweight and efficient. So this is our code we used in this prototype. Now, if we see the task manager after our using a prototype, we can observe that the system behavior from the manager. We can see how CPU and memory usage are being monitored and the system remains stable while our responsiveness guard is active. So, to stop this cluttering with intelligent analysis, our system helps in identifying and preventing performance degradation before it affects the user experiences. Although a prototype operates at the user level, it demonstrates how a kernel-aware responsiveness guard can function. In real-world scenario, this mechanism can be integrated with the OS kernel to dynamically adjust process priorities and resource allocation, thereby improving overall system responsiveness. Now I will briefly highlight the key design decisions of a system. Firstly, we adopted a proactive monitoring approach where the system continuously observes CPU, memory and process behavior instead of waiting for failures. Second, we use threshold based and logical analysis to accurately detect and potential slowdown conditions. Third, our system follows a modular architecture, making it easier to extend and upgrade. Fourth, we ensure that the solution is lightweighted and performance friendly so it does not have extra overhead. Finally, our architecture is future ready and can extend it to kernel level optimization and intelligent prediction mechanism. So, our system responsiveness guard provides a smart, efficient, and scalable approach to preventing system slowdowns. It not only detects performances issues but also provides a foundation for intelligent kernel optimization. This solution can be applied in personal computers, enterprise systems, and also in cloud environments. So, in future, this system can be extended with machine learning modules and deeper kernel integration and also automated control mechanisms to make it even more powerful. So hereby I conclude my presentation. Thank you for watching my presentation.